So I'd like to do a short review of about the last 20 minutes from class for week 1. And I'd like to start off with the chart, which is figure 2-14 on page 48 of your book, because I think it encapsulates a lot of the main concepts that we wanted you to take away from chapter 2. So let me start off in the upper left-hand corner with the sun. Now we said that the sun is emitting energy across all wavelengths on the electromagnetic spectrum, but in terms of what it does to heat the surface of the earth, we're going to talk about shortwave radiation that is emitted from the sun and is absorbed by the surface of the earth, and that's depicted by the yellow squiggly lines here on the left. As the surface of the earth heats up, it's in physical contact with air molecules right above the surface of the earth, and that energy from the surface of the earth, that heat energy, is transferred to those air molecules and starts warming the air. Now as that air is warming by the process of conduction, it becomes more buoyant and it rises up away from the surface of the earth through the process of convection. A parcel of air, if you think about it, it's like a balloon of air, as an analogy, starts to rise because it is now warmer than its surroundings. And as it goes up in the atmosphere, it's experiencing a drop in pressure, because as you go up in the atmosphere, remember, pressure falls. As the parcel goes up with less pressure on the outside of it, the molecules are able to push out from the inside, and the volume of the parcel increases. As the volume increases and pressure decreases on the outside, the temperature starts to decrease as well. And those are ruled by the ideal gas law that drives that, and we'll talk about that more in future lectures. So we started off again with the process of conduction, heating the air. It turns into transitions to the process of convection. Air rises via convection to a point where the parcel is cooling off as it's going up in the atmosphere, and it cools to a point where the water vapor gas now condenses to a liquid. And at that point where the phase change happens from gas to a liquid, we release heat, and we call that a latent heat release. That latent heat heats the environment. It's an actual, you can measure a temperature rise as a result of that. And the parcel continues to rise through upward into the atmosphere until a point where it reaches, where it's cool enough that gravity pulls it back down towards the earth. Now, that parcel of air that starts to sink is encountering increasing pressure on the outside of it, and the parcel starts to be compressed. As the parcel's being compressed, the temperature on the inside starts to increase. So, quick review here. Parcels that rise tend to expand and cool. Parcels that are pushed back down towards the earth are compressed, and then they warm up. And that parcel gets wrapped up in a convective circulation for one or many more times, depending on how much heat energy is stored inside that cloud. So on the right-hand side of the diagram, we have red squiggly lines, and those are depicting long-wave radiation being emitted from both the surface of the earth and also from gases in the atmosphere, specifically water vapor and carbon dioxide. So we'll call this line number 1, and this will be line number 3. We see that they're continuous lines from the surface of the earth going up into space. So we have a long-wave radiation being emitted from the earth that is unimpeded and going straight out into space. We'll say this is line 2 and this is line 4. Those lines are discontinuous. We see they have a break in the middle of the line, and that break is representative of water vapor and carbon dioxide that has absorbed solar radiation. And some of that energy is emitted upward from water vapor and carbon dioxide back into space, and some of that energy is emitted back downward towards the earth. This energy that's emitted back down towards the earth warms the earth's surface from above as that emits downward. So we moved on from this general model here, and we looked at the basic fact that if we had 100 units of inbound radiation, and 100 is just a good round number, about half of the inbound radiation is absorbed at the surface of the earth. About 19% is absorbed by the atmosphere and by clouds. So water vapor, carbon dioxide are absorbing about 19% of that. The remaining 30% is either reflected back into space or it's scattered across throughout the atmosphere. And the word we use to describe reflected energy is the amount of albedo something has. So the tops of clouds that are bright white reflects a lot of energy. We'd say it has a high albedo. The surface of the Earth, which may be covered with darker colors, greens, browns, blacks, that actually absorb energy, they have a low albedo. They don't reflect a lot. If you had a snow field on the surface of the Earth that's undisturbed, then you'd have a lot of reflection of energy. And so a snow field has a high albedo. We broke this diagram down even further, and we used added on to here what are some of the various means that you can release energy and gain energy. So the first thing I want you to take away from this is notice across the bottom that the energy gained at the surface of the Earth equals the energy that's lost from the surface of the Earth. So this energy balance has to occur. In terms of how do you lose energy at the surface? Through the process of convection and conduction. If you remember the definition, conduction is when we transfer heat by touching. Convection is by transferring heat by the process of parcels rising in the air, cooling and expanding, or compressing and shrinking in size. We also lose heat through the process of latent heat, when we have water that's evaporating from the surface and condensing into clouds above. And then finally we have outbound radiation. This is long-wave radiation that is coming off the surface of the Earth and going back into space. And then of course on the right-hand side we have various methods of inbound radiation. So we have the direct solar short-bound radiation. About half of the solar inbound radiation is absorbed in the Earth, and then the rest of the amount is long-wave radiation that's re-emitted back towards the Earth. On average across the surface of the Earth, we stated yesterday that across the tropics we actually have a surplus of incoming radiation. So we take in more energy than we pass back into space. At the poles it's directly opposite. We actually radiate out more long-wave radiation than we bring in. And that kind of makes sense because we don't have direct solar radiation on the North Pole or South Pole as consistently through the years with the tropical latitudes. There is a transfer of heat from about the equator going northward and the equator southward, and in a few chapters from now we'll talk about how that energy is transferred. But for now, just understand that on average at the poles we have a deficit, and at the equator and the tropical latitudes on average we have a surplus of energy. We also talked briefly about space weather, and this will be the only time we actually cover in depth any space weather in this course. So let me just kind of review what we were talking about. We did go over the various parts of the sun, and we said that at the core of the sun we have gases that are going through nuclear reaction that generates energy. We said that the sun is emitting across all wavelengths of the electromagnetic spectrum. The very fact that we can see the sun indicates that it's at least emitting through the visible portion of the spectrum, but it also is emitting on highly charged particles of energy, or streams of ions from the surface of the Earth. From the surface of the sun towards the Earth. That stream of ions is what we call the solar wind. Now, at the Earth, facing the sun, we have magnetic field lines that, when they're not disturbed, they're uniformly distributed across the surface of the Earth. In this particular diagram on the right, we have the magnetic field lines flowing from the southern hemisphere into the northern hemisphere. And the pattern on these magnetic field lines looks very similar to what we'd see on a bar magnet with polar opposite ends. It doesn't matter in this particular case that the bar magnet is going in the opposite direction of the Earth. What we want you to take away here that it is the uniform distribution of the magnetic field lines when they are undisturbed by anything from space. Now, when the sun releases a large stream of those charged particles in this, we call that, this is the solar wind right here. There's a pressure force that's put onto those magnetic field lines, and the magnetic field lines go from a nice uniform distribution that you saw on the previous chart to a deformed state. So the side of the Earth that's facing the sun has the magnetic field lines compressed, and on the side of the Earth that's not facing the sun, we have the magnetic field lines stretched out into a long tail. Now, some of the charged particles slip in between the magnetic field lines going into the northern and southern hemisphere, and these charged particles go into the atmosphere and start energizing the molecules that we have in the ionosphere. So as a charged particle comes in from space, it hits the electrons that are orbiting around the protons. And what we end up having is that energy causes the electron to go from a lower state, a lower orbit, to a higher orbit. And this change from a lower orbit to a higher orbit is adding energy to the electrons. Now, if you remember from chemistry, nature doesn't like that. It wants all the electrons in the lowest possible orbits. So remembering that energy cannot be created or destroyed, the energy that was gained by this electron, when it is brought back down to a lower orbit around the protons, has to be transferred into transitioned into some other type of form. In this particular case, when that electron comes from a higher state to a lower state in the orbital plane, it releases light. That's the energy that it's transferred to. And we call that light that comes off of it a photon. Now, with a stream of charged particles in the ionosphere doing this, what we end up with is the Aurora Borealis, as depicted here, and we can actually end up with a Borealis equivalent down in the southern hemisphere as well. So what you see here, the dancing shades of light that are in the sky, those are charged particles in the ionosphere that are being charged by the solar wind. Now, across the North Pole, at least, we have the geographic North Pole that sits exactly where the 90 degrees north latitude culminates at. But we also have the magnetic North Pole, and that is offset slightly from the geographic North Pole. The auroral oval, which is depicted by this red line, this is where the bulk of the charged particles we see with the Aurora Borealis are centered around. It has the magnetic North Pole at the center of the ring. Okay, and with it being offset from the geographic North Pole, this entire region is offset in latitude. So if we look down, for example, across the state of Maine, the state of Maine lies on about the same latitude line as the state of Washington. But because of this offset that we have here from the geographic North Pole to the center of the auroral oval, we have a higher probability of seeing the northern lights or the Aurora Borealis in Maine than I do in Washington State, even though they're on the same latitude. So just understand that this offset between the North Pole and the magnetic North Pole is the reason why we'll see the Aurora Borealis at different locations, even though they're on the same latitude lines. I'd also like to point out that it is very possible for us to predict when these Aurora Borealis or solar events happen. We have solar observatories at various places around the Earth that are tracking the sunspots as they rotate around the solar plane. When we see the sunspots rotate around, based on where they are on this sphere, we can predict by about a day or two when those charged particles from the solar flare are going to reach the Earth. So, for example, if you were to, if a solar flare erupts, you're not immediately going to see the Aurora Borealis kick in. There is a delayed response, and since we can forecast that, we can accommodate that. And if you remember, some of the impacts from the solar wind and the Aurora Borealis have high impact on communication signals that flow through the ionosphere. This was my review for the class. I have nothing further to add from this. If you have any questions about what I've just presented, please send me a note, and I'll be more than happy to explain it to you. Thanks.